Everyone, welcome back to my channel. This is the second video for my podcast where I'm doing the little tidbits about the organic chemistry to make to understand the interesting stuff, right? So we are going to do today about to know the difference between lithium aluminium hydride and sodium borohydride. We all know that lithium aluminium hydride is a very powerful reducing agent, whereas sodium borohydride is very mild reducing agent. Sodium borohydride you would have seen we use in methanol, we use in water. So simple, like you just take out like balls. You can keep in the hand. It's very simple. It's a very mild reducing agent. But LiAlH4 is very powerful, very reactive. You open the bottle, you have to open in the nitrogen atmosphere and use it immediately. As we know, NaBH4 reduces basically aldehyde and ketone and also acyl halide. But it will not reduce acid and acid derivatives. But when you take lithium aluminium hydride, it will reduce everything. It will reduce acyl halide to alcohol, aldehyde to alcohol, ketones to alcohol, acid to alcohols, amides to amines, and esters to alcohol, right? So we want to understand why so much difference is there. Before we understand the difference, let us understand first of all why are they reducing agent at all, right? The thing is both of them are hydride donors. Now if you think that they give H minus separately, now we know H minus cannot go and reduce. If you use sodium hydride, will it ever reduce either any of them? Never, because H minus is so small in size that it will not be able to overlap with pi star orbital of the aldehyde ketones or the acid derivatives. Please understand, when we are talking about a nucleophilic attack, we are talking about orbital interaction. When we talk about acid base interaction, it is more of charge interaction. So this lobe has to be bigger so that it can go and attack. So if it is not hydride, then what is that goes and attacks? So basically it is the sigma bond. It is the sigma bond which is nucleophilic. So the BH sigma bond or the ALH sigma bond, these two are nucleophilic, and that's what is responsible. So let us see here. So this is lithium aluminium hydride and this is sodium borohydride. Now what happens, kind of salt. So lithium plus is there, aluminium has negative charge. Now because aluminium has negative charge, all the sigma bonds on the aluminium are nucleophilic in nature. They are electron dense in nature and therefore they can give away electrons. Similarly in borohydride, because boron has negative charge, all the bonds from the boron, that is all these BH bonds, are nucleophilic in nature. Now what happens? Now if you see, hydrogen electronegativity is 2.2, whereas aluminum is 1.6 and boron is 2.0. That means hydrogen is more electronegative than these two. So what happens when the sigma molecular orbital is there? The sigma molecular orbital is closer towards hydrogen than aluminum because hydrogen is more electronegative. Similarly, again here the sigma bond is closer towards hydrogen, and therefore when they attack, it will be the H minus which is attacking. So sigma bonds, sigma bonds are rarely nucleophilic, but here the sigma bonds are nucleophilic because boron is having negative charge, aluminum is having negative charge, and most importantly there is electronegativity difference between aluminum and hydrogen or boron and hydrogen, right? Now we know for any mechanism, for any nucleophilic attack, what happens? The nucleophiles HOMO, highest occupied molecular orbital, goes and attacks at the lowest unoccupied molecular orbital of electrophile. So HOMO of nucleophile attacks the LUMO of electrophile. So that means the nucleophile needs highest energy, and the electrophile orbital which accepts the antibonding molecular orbital should have lowest energy. It's like whoever is more rich will be able to give more money, right? So whichever is having higher energy will be able to give electrons as nucleophile, and whichever is poorer has the more chances of getting money, right? So similarly the molecular orbital which has lowest energy, the antibonding molecular orbital, they are better electrophiles. Now, if we talk about orbitals, when the lone pair of electrons are there, they are having much more energy than your pi bond, and pi bonds have much more energy than your sigma bond. So sigma bond very rarely you would have seen they are nucleophilic. In this case they are nucleophilic. So something like when you have oxygen you have on ketone, you would have seen they go and attack sometimes. So it's always the lone pair, not the pi bond. Okay, if lone pair is not there, then only pi bond will go and attack. And then we have seen most of the cases you will see is the lone pair which is nucleophilic. Sometimes when they have negative charge, they are much more nucleophilic because of negative charge they are unstable, very high energy. But pi bond is more stable because it's a bond. So when it is more stable, it has lower energy. And then last is sigma bond, because again bond very well established between two atoms, so they are least nucleophilic. So but when do we see sigma bonds as nucleophilic? They are nucleophilic at some cases. Example, when you talk about organolithium compounds or your organomagnesium compounds, organomagnesium bromide, that is Grignard reagent, right? Again I'll tell you, it's not Grignard, it's Grignard reagent, because it's a German name, it's a proper noun, so we have to pronounce it according to that. So what happens here is, basically if you see lithium's electronegativity is 1, carbon's electronegativity is 2.5. So that means lithium is more electropositive than carbon, or carbon is more electronegative than lithium. So what is electropositive? Lithium is more electropositive means it gives away electron to get positive charge. So what happens here basically is, lithium gives away its electron towards carbon. So when you see the molecular orbital picture, the electrons are not equally distributed. The sigma bonding molecular orbital is closer towards carbon, and therefore carbon has negative polarity and lithium has positive polarity, and therefore when the attack occurs, it is via the carbon which it occurs, and it attacks this carbon and this I minus leaves, and you get this sigma bond. Very similarly here also, magnesium being a metal is more electropositive than carbon. What is the electronegativity of magnesium? 1.3, much lower than carbon. Carbon is 2.5. So it is electropositive. That means magnesium gives away electron. The molecular orbital, this sigma bond, this is a molecular orbital, is closer towards carbon, and therefore carbon is this sigma bond is nucleophilic, but bond is closer towards carbon, therefore this carbon goes and attacks, and therefore this happens. And now you see the difference. What happens is, electronegativity difference between these two is greater than between magnesium and carbon, because carbon is anyway 2.5 for both of them, but here lithium is 1, magnesium is 1.3. So lithium is more electropositive, it gives away more electron to the carbon, and therefore organolithium is more reactive, much more nucleophilic than your Grignard reagent. Very similar. So what we basically are saying is, when more electropositive atom is attached to the counter atom, more electrons are donated towards the electronegative counter atom, making the sigma bond more nucleophilic. So similarly what happens is, in LiAlH4 and NaBH4, aluminium has electronegativity of 1.6, boron has 2.0, hydrogen was 2.2. I'll go back to the picture so it makes more sense. Yeah, so lithium is sorry, not aluminum, boron we are considering. So aluminium was 1.3, I guess. Just one second, let me check once again. 1.6, right? So lithium is 1.6, hydrogen is 2.2, and boron is 2.0. So very clearly if you see the difference between aluminum and hydrogen, hydrogen is more electronegative, electrons are closer towards hydrogen, but aluminum is much more electropositive than hydrogen, so gives away all the electron towards hydrogen. You understand? First comes boron, then comes aluminium. So as we know, when you go down the group, they are in the same group, group 3, okay? So when we go down the group, electronegativity reduces, or you can say electropositivity increases. Aluminum is much more electropositive than your boron, and therefore gives away all the electrons to hydrogen, and therefore this sigma bond becomes much more nucleophilic, and therefore they are able to attack all the carbonyl groups of the aldehyde, ketone, acid and acid derivatives, even amides, ester will reduce. But boron and this, see the difference is hardly anything. Boron is 2.0, hydrogen is 2.2. But because boron has negative charge, this bond has become um, nucleophilic, and hydrogen having little more electron than boron, very little, because it's 2.2 and 2.0, hardly any difference is there. But that little bit difference is what makes it a nucleophilic, and that's why they give the hydrogen bond. So whenever you show a mechanism, let me show here. When you show the mechanism, oh, I have not shown, I should have shown, okay? So let me draw it here. So whenever you show the mechanism, you cannot show separate H minus, you have to show via sigma bond, because the sigma bond is nucleophilic. You cannot think as hydride donor that you show it as H minus and then you show the attack. This will be a disaster mechanism, absolutely unacceptable, okay? This cannot happen. You have to show because this sigma bond is nucleophilic. I hope I made sense. So that's the last part of it. So lithium aluminum hydride is much more powerful reducing agent than sodium borohydride. Thank you very much.